Salam everyone. In this video I am going to explain the concept of relation, but before explaining relation I would like to explain the Cartesian product of two sets. So first I will explain Cartesian product of two sets, and then on the basis of that I will explain the concept of relation. So let's start with the Cartesian product of two sets. So let A and B are two non-empty sets, then Cartesian product A cross B is the set which contains all the possible ordered pairs A comma B such that small a belongs to set A and small b belongs to set B. That is, first component of the ordered pair belongs to set A and second component of ordered pair belongs to set B. For example, A is a set 1, 2, 3 and B is a set 8, 9. So A cross B will be the set of ordered pairs 1, 8, 1, 9, 2, 8, 2, 9, 3, 8 and 3, 9. So you see, in every ordered pair, first component belongs to set A and every second component of the ordered pairs belongs to set B. So if we find B cross A, then all these ordered pairs will be reversed. That means first ordered pair will be 8, 1, second ordered pair will be 9, 1, then 8, 2, then 9, 2, then 8, 3 and then 9, 3. Now every first component of ordered pairs belong to set B and every second component of ordered pairs belong to set A. So it is obvious A cross B is not equal to B cross A. That is, Cartesian product is not commutative. Now let us talk about relation on the basis of Cartesian product. If A cross B is a Cartesian product, then any subset of A cross B is called a relation from A to B, which is denoted by R colon A arrow B. R is the relation from A to B. Here A is said to be domain of R and B is said to be codomain of R. Now let us talk about the range of relation R. The range of R is the set of all those elements of codomain B which have association with elements of set A. Example, if A is the set of 1, 2 and B is the set of 8, 9, 10. So A cross B will be set of ordered pairs 1, 8, 1, 9, 1, 10, 2, 8, 2, 9, 2, 10. So any subset of Cartesian product, say R1 is the set of 1, 8, 2, 8 and 2, 10. So obviously this is a subset of A cross B because each and every component of R1 is contained by A cross B. 1, 8 is here, 2, 8 is here and 2, 10 is here. So this is a subset of A cross B. That's why we call it a relation and we denote it by R1. So any subset, you may take different subset. So for example 1, 10 and 2, 10. So this is also a subset of A cross B, so it is said to be a relation from A to B. So R1 and R2 both are relations from A to B. So we may write it as R1 is a relation from A to B and R2 is also a relation from A to B. Now we have to talk about the relation in a set. If a relation has domain and codomain same, that is, if domain and codomain of a relation is the same set, it is said to be a relation in a set. A is said to be a relation in a set A. Similarly, if relation has domain B and codomain is also B, that is said to be a relation in a set B. Now we have to talk about different types of relation in a set. So types of relations in a set. There are three types of relations in a set. First one is reflexive relation. Second, symmetric relation. And the third one is transitive relation. First, reflexive relation, second, symmetric relation, third, transitive relation. Now, a relation can be reflexive relation but not symmetric, not transitive, or it can be reflexive and symmetric but not transitive, and it can be reflexive, symmetric as well as transitive. And it is also possible that a relation is neither reflexive nor symmetric nor transitive. So if a relation is a reflexive relation, symmetric relation as well as transitive relation, it is said to be an equivalence relation. Now let us talk about reflexive relation in detail. A relation R from A to A is said to be a reflexive relation if for all A belongs to A, there must exist A comma A in R. That is, each and every element of domain is related to itself. If this characteristic is satisfied by a relation, it is said to be a reflexive relation. For example, if A is the set of 1, 2, 3 and B is a set of 7, 8, 9, R1 is a relation from A to A such that R1 is defined as the set of ordered pairs 1, 1, 1, 3, 2, 2, 2, 3, 3, 3. So if we consider R1 and we have to check the reflexivity of the relation, we have to check whether each and every element of A is related to itself, because this is relation from A to A. So if each and every element is related to itself, that means there is 1, 1 and there is 2, 2 and there is 3, 3. So that means each and every element of domain A is related to itself. So R1 is a reflexive relation. It doesn't matter then, except these three ordered pairs 1, 1, 2, 2, 3, 3, how many other ordered pairs exist or not. So R1 is a reflexive relation since 1, 1, 2, 2, 3, 3 belong to R. Now let us suppose R2 is a relation B to B. B is a set 7, 8, 9 and the domain and codomain of R2 is the same set B, 7, 8, 9. So R2 must be a subset of B cross B. So let R2 is defined as ordered pair 7, 7, 7, 8, 8, 9, 9, 9. So if we check the reflexivity of R2, according to definition, each and every element of B should be related to itself 7, 8, 9. So there should be 7, 7, 8, 8 and 9, 9 in R2. Then it will be a reflexive relation, otherwise it is not. So if we observe 7, 7 is there, that means 7 is related to itself, and 8, 8 if we observe there is no 8, 8, that means one element of B is not related to itself, though 9, 9 is there. So 7 and 9 both elements are related to themselves, but there is one element 8 which is not related to itself. So that means this is not a reflexive relation, because one element is violating the characteristic of reflexive relation. So R2 is not reflexive because 8, 8 does not belong to R2. Now let us talk about symmetric relation. A relation R from S to S is said to be a symmetric relation if for all A, B belongs to S, if A, B belongs to R, then it implies that B, A also belongs to R. That means if we interchange the components of any ordered pair, that must also be contained in the relation. Or in other words, you may say the rotation of every ordered pair must be contained in the relation. So if there is A comma B, there must be B comma A in R. Then it is said to be a symmetric relation. And if any ordered pair violates this criterion, the relation will not be a symmetric relation. For example, if R is a relation S to S, where S is the set of 1, 2, 3, 4, and R is defined as set of ordered pairs 1, 2, 1, 3, 2, 4, 2, 1, 3, 1, 4, 2, 4, 4. So if we observe each and every ordered pair, and if we check its reverse, that means if we interchange the component of this ordered pair, it will be 2, 1. So 2, 1 is there. If we interchange the components of this ordered pair 1, 3, so there must be 3, 1. So it is also here. And reverse of this ordered pair 2, 4, that is 4, 2, it is here. So if we interchange the elements of this ordered pair will remain the same. So we may say that reverse of this ordered pair is also contained by the relation. So we may say that inverse of every ordered pair is contained by the relation. That's why the relation is said to be a symmetric relation. So R is a symmetric relation. Now we are going to discuss transitive relation. So let's start. A relation R from set S to S is said to be a transitive relation if for all A, B, C from the set S, if A comma B belongs to R and B comma C belongs to R, then A comma C must also belong to R. That means if there are two ordered pairs in a relation such that the second component of one ordered pair is identical to first component of some other ordered pairs, then the first component of the first ordered pair must be related to the second component of second ordered pairs. For example, A is a set 1, 2, 3 and R is a relation from A to A. And R is defined as the set of ordered pairs 1, 2, 2, 3, 1, 3. Obviously, this is a subset of A cross A. So this is a relation from A to A. So if we observe in these two ordered pairs, the second component of this ordered pair is identical to first component of this ordered pair. So according to criterion of transitive relation, the first component of this ordered pair must be related to second component of this ordered pair. That is 1, 3 must be contained by the relation, which is here 1, 3. So we may say that R is a transitive relation. So R is a transitive relation. Here we must note down one thing which is very important. If this kind of situation is not there, that is the second component of any ordered pair is equal to first component of any other ordered pair, that means the transitivity cannot be checked. And if transitivity of a relation cannot be checked, it is also considered to be a transitive relation. So if transitivity of a relation cannot be checked, it is considered to be a transitive relation. And now we come to equivalence relation, and as I said, if a relation is symmetric, reflexive and transitive, it is said to be an equivalence relation. So equivalence relation is defined as if R is a relation from A to A, it is said to be an equivalence relation if it is reflexive, symmetric and transitive.